Most of the modern anesthesia departments use newer workstations. However, the departments, particularly in medical colleges and teaching institutes, would have one of this purely from an academic point of view. This is the basic Boyle's machine, and as you see, the stainless steel tray on the counter, if you lift it up, you will find a device which looks like what is represented in the picture next. This is a pressure regulator. Welcome to this episode of Doodles, wherein we are going to talk about pressure regulators. What are pressure regulators? Why do anesthesia machines have these pressure regulators? How do they work? So this is what we are going to talk about over the next few minutes. These pressure regulators literally regulate pressure. As highlighted in the previous slide, they're very easy to see. The moment you lift the stainless steel tray on the counter, you will see them. But in the modern anesthesia workstations, you might not see them that easily, but they are very much present. One of the principal reasons why we need pressure regulators is the disparity between the supply pressure and the working pressure. We all know the oxygen cylinders are generally pressurized to a pressure of around 2000 psi, while the working pressure, which is fed into the intermediate pressure system of the anesthesia machines, is about 50 psi. This is further reduced before it's fed into the low pressure system. The necessity to keep the working pressure low is mainly to protect sensitive equipment present in the intermediate and the low pressure system on the anesthesia machine, which can be damaged if they are subjected to higher pressure. If the sensitive equipment in the anesthesia machine needs a low working pressure, why at all have high supply pressure? Most of the hospitals rely on centralized supply of gases, wherein we have type H cylinders on the manifold or a liquid oxygen plant. Oxygen coming out of it passes through a pressure regulator, which brings it down to a 50 psi pressure, which is supplied to the machine. Alternatingly, we have a type E cylinders on the machine which act as backup. But for the purpose of discussion, let us assume that we are relying entirely on these type E cylinders attached to the machine to supply oxygen. So let us say a case is going on under general anesthesia. We are having an oxygen flow rate of around 1 liter per minute. We are having a minute ventilation of around 5 liters per minute. The ventilator uses oxygen as drive gas. So combining the fresh gas and the oxygen needed to drive the ventilator, we end up using about 6 liters of oxygen in a minute. Suppose a case runs for about 90 minutes or 1.5 hours, we end up using about 540 liters of oxygen. So we all are familiar with this a water tank which we see on top of our houses. So this is about a 500 liter capacity tank. It has got a diameter of about 3.5 feet and a height of 3.5 feet. Imagine having a tank like this in the operation theatre, and imagine the amount of space it occupies. Imagine it running out every 1 hour, 1.5 hours, and having to fill it again repeatedly. This can be quite cumbersome and painful. This is where Boyle's law comes to our rescue. Boyle's law states that at a constant temperature, pressure and volume are inversely proportional to each other. So if we increase the pressure of a particular volume of gas, its volume comes down. Contrarily, if the pressure is reduced, the volume increases. So using this principle, 660 liters of oxygen is pressurized to about 2000 psi, wherein its volume can be shrunk and accommodated in a type E cylinder which has a volume of around about 5 liters. Now, when the oxygen comes out of the cylinder, passes through the pressure regulator and reaches atmospheric pressure, it increases its volume back to 660 liters. So thus pressure regulators do their principal function, which is to reduce the pressure. What happens if they just end up reducing the pressure only? So as the cylinder starts emptying, the input pressure into the pressure regulator keeps coming down, as a consequence of which the output pressure also constantly keeps coming down. As a result of this, we'll end up constantly altering the flow meter, adjusting the flow meter in order to keep the flow constant, which is again a problem. This brings us to the second point which the pressure regulators do, that is to keep the output pressure or the working pressure constant irrespective of what the input pressure is. So thus they function like the voltage stabilizers protecting sensitive equipments at home. So they essentially what they do is convert a high and a variable pressure to a low and a constant working pressure. So over the next few slides, with certain numerical examples, we'll see how pressure regulators do both of these. Before we move any further, we just need to clarify one more concept, which is the relationship between pressure and force. So if you all remember, if we need to unblock a cannula which has got a blood clot at the tip, which of the two syringes would we prefer? The natural choice would be a 2 ml syringe. The reason being, for a given amount of force which is applied on either of the syringes, because the 2 cc syringe has a smaller cross-sectional area, a much higher pressure is generated, which can effectively dislodge the clot or a blockage. This brings us to the equation that pressure is equal to force applied over a particular area, or pressure is equal to force divided by the area over which the force is acting. Rearranging this equation and solving for force, we get force would be equal to pressure multiplied by the area over which the pressure is acting on. Please remember this important concept, because this is what essentially is used in the pressure regulator. We all go shopping, be it groceries, vegetables, or fruits, or anything. One of the way the shopkeeper dispenses is weighing these in a weighing balance. So here we have one such balance. Imagine a force F1 and a force F2 are acting on either side of the balance. Depending on which force is higher, the balance would tilt to that side. But if both the forces are same, it would be equally balanced without tilting to either of the side. Now what is this force F1? So this force F1 is generated by a pressure represented here as PC acting on an area A1, while the force F2 is generated by PR pressure acting on an area A2. Now, going back to the principle, force is pressure applied or acting on a particular area. So here, if we take PC as the cylinder pressure, which is a high pressure, suppose if we make it act on a much smaller area, A1, we can generate a force which would be similar to force generated by PR, which is the regulated pressure coming out of the pressure regulator, acting on a much larger area, A2. Thus, the pressure regulators, by balancing the forces generated by a larger pressure acting on a smaller area and a smaller pressure acting on a larger area, they're able to reduce the pressure. In the subsequent discussions, when we highlight the functioning of the pressure regulator with numerical examples, we will be principally talking about the first stage pressure regulators, wherein pressure is reduced from 2000 to 50 psi. The second stage pressure regulators, which are present in the anesthesia machine, reduce this pressure further from about 50 psi to about 14 psi before it is fed to the flow meters and subsequently onto the low pressure system. So over the next few slides, we will be doing a lot of calculations to understand how exactly the pressure is reduced, not only reduced, but also how the output pressure is kept constant. Please feel free to pause the video while you're doing the calculations. A couple of points. I have omitted the units of force, just kept few numbers so as to make it easy to go through the calculations and understand. Please do keep this in mind. In the next slide over here, we have a line diagram representing the internal functioning of a direct acting pressure regulator. We have a regulator in the middle. On the left side, we have a cylinder and a pressure gauge to measure the cylinder pressure, a tube leading into the pressure regulator. On the other side, we have a tube leading out of the pressure regulator and a stopcock regulating the flow, a second pressure regulator representing the reduced pressure PR. Now, to begin with, there is no gas inside the regulator. When we open the cylinder using the key on the far left side, the cylinder pressure is recorded in the pressure gauge shown there as cylinder pressure PC. So because of the flow, the gas flows into the pressure regulator, acting on a small area A1, generating a force which lifts the area A1 away from the tube leading into the pressure regulator, thereby allowing the gas to flow into the regulator. The space represented as R in the diagram. As gas starts filling up in the area R or the volume R, its pressure slowly starts increasing. Once it reaches the pressure PR, this pressure acting on area A2 generates a force which is equal and opposite to the force generated by cylinder pressure acting on area A1, thereby shuts off further inflow of gas from the cylinder into the regulator. Now, if we disturb this equilibrium by opening the stopcock, a certain amount of gas is let out of the pressure regulator. This results in PR decreasing slightly. As a result, the force generated by PR acting on A2 would be slightly less than the force generated by cylinder pressure acting on area A1, as a result of which some more gas is let in from the cylinder into the pressure regulator, restoring the pressure back to PR. This happens in a smooth and a continuous fashion, gradually emptying the contents of the cylinder. Having understood how a direct acting pressure regulator works, let us put some numbers into these equations. So the first equation we have is the equation which balances both the forces. the force generated by the cylinder pressure PC acting on area A1, and force F2, which is the regulated pressure PR acting on area A2. If we rearrange the equation solving for the regulated pressure PR, we get the regulated pressure PR is equal to the cylinder pressure multiplied by area A1 divided by area A2. Now we know the regulated pressure coming out of the first stage pressure regulator is 50 psi. And generally, if you take the oxygen cylinder, the cylinder pressure is around 2000 psi. That leaves us with the equation 50 is equal to 2000 times A1 by A2. If we have to put some numbers into this A1 and A2, that would be A1 would be equal to an area of 1 unit. A2 should be 40 times that area. That would give us a solution to this equation. Thus, the area ratio of 1:40, that is, area of A2 being 40 times the area of A1, would balance both sides of the equation. Thus, with this example, we're able to see how the pressure is reduced. But what happens if the cylinder pressure reduces by half, the cylinder empties by half? The cylinder pressure drops to 1000 psi. When we feed this into the equation, we find that the regulated pressure drops from 50 to 25. So what happens if the cylinder is only 1/4 full? So the cylinder pressure drops to 500, and when we solve the equation, we find that the regulated pressure drops to 12.5. So this makes sure that the pressure is reduced, but the output pressure is not kept constant. As the input pressure or the cylinder pressure is coming down, the regulated pressure, the output pressure is also constantly coming down. How do we keep this output pressure constant? Now, this is ensured by addition of a spring S1 to the pressure regulator, which generates a force Fs1. So if you look at the line diagram here, you can see the spring S1 compared to the earlier version, wherein it was only force F1 which was facilitating entry of the gas into the regulator, and force F2 was opposing it. In the current iteration, the Fs1, force generated by spring S1, also favors or facilitates entry of gas into the regulator. This alters the balance of forces, facilitating and opposing entry of gas into the regulator. So if we have to rebalance, a new equation will have to be written. So this is force F1, that is PC acting on area A1, cylinder pressure acting on area A1 plus the force generated by spring S1 would be equal to force F2, that is the regulated pressure acting on area A2. Now, the force generated by spring S1 is of such a large magnitude as compared to the force F1 that any change in F1, which is a resultant of variations in the cylinder pressure, will not have any significant impact on the sum total of forces facilitating entry of gas into the pressure regulator. Now, the area A2 on which the regulated pressure act has to increase significantly as compared to earlier in order to address this, increase the force generated by spring S1 and balance the equation. Now, this area A2 is predominantly determined by the force generated by spring S1. The closest analogy we can give to this is switching on street lights in the middle of the day. Now, the brightness of the sun is so high that it doesn't matter whether the street light is switched on or off, or you alter the intensity or brightness of the light. That is not going to have any significant difference to the brightness what we are going to see. So if we have to rewrite the equation balancing the forces facilitating entry and opposing the entry of gases into the pressure regulator, we get this new equation as noted in the previous slide. PC times A1 plus force Fs1 would be equal to PR times A2. Rearranging this equation for the regulated pressure PR, we get PR would be equal to cylinder pressure PC acting on A1 plus force of spring S1 divided by area A2. Now if we start putting some numbers into this, we know the regulated pressure, as I noted earlier, is 50, cylinder pressure as 2000. Let us assume the force generated by spring S1 to be about 1 lakh units. So with this, the area A2 has to increase significantly. While it was 40 in the earlier equation, the current equation, it has to be around 2040 in order to solve this equation. So let us see what impact this has on reducing the cylinder pressure. Suppose the cylinder pressure comes to 1000 psi, that cylinder becomes half empty. So the 2000 becomes 1000. So the impact it has on the regulated pressure PR is only about 0.5. The regulated pressure drops from 50 psi to about only 49.5 psi. What happens if the cylinder is 3/4 empty? That's only about 500 psi of pressure. So if we solve this equation, we get the regulated pressure to be around 49.25. So even though the cylinder pressure dropped from 2000 psi to 500 psi, the regulated pressure or the output pressure the regulator is putting out, or the working pressure, drops only from about 50 to 49.25. Thus, apart from reducing the pressure regulator also stabilizes the output or the working pressure, keeping it constant. So far, we have had a look at direct acting pressure regulators. So in this slide, we have a line diagram representing the functioning of an indirect acting pressure regulator. Now compared to a direct acting pressure regulator, so the only difference is both the cylinder pressure acting on area A1 as well as the regulated pressure acting on area A2 would oppose the entry of gas into the regulator, while the force generated by spring S1, Fs1, would be the only one facilitating entry of gas into the regulator. Thus, the balancing equation can be rewritten as the force generated by spring S1 would be equal to cylinder pressure acting on area A1 plus the regulated pressure acting on area A2, that is the sum of force F1 plus F2. Thus, as noted earlier, if we were to write a new equation for an indirect acting pressure regulator, the forces opposing and facilitating entry of gas into the pressure regulator, the equation would be as noted here. Rearranging the equation and solving for regulated pressure, the rearranged equation would be regulated pressure would be equal to force of spring S1 minus cylinder pressure acting on area A1 divided by area A2. Putting in some numbers, the cylinder pressure being 50, let's assume the force of spring S1 is 1 lakh units, the cylinder pressure being 2000. Solving for this equation, the new area A2 works out to be 1960 times the area A1. So I'll leave you to do the rest of the calculations. The only significant thing you would note is, as the cylinder pressure comes down, the regulated pressure marginally increases. To conclude, let us have a look at a cross-sectional diagram of an actual indirect acting pressure regulator, which are the most common types of pressure regulators used. Here we can note that the cylinder pressure, the gases coming from the cylinder as indicated by high pressure inlet capital P, enters from the bottom left, acting on a valve seating area lowercase a, represented as area A1 in the line diagram. The lower pressure outlet, lowercase p, is the regulated pressure coming out of the pressure regulator. And the diaphragm A, area A, capital A, on which the regulated pressure acts, which is the equivalent of area A2 in the line diagram. Now, both these forces, which are generated by the cylinder pressure acting on the smaller area A and the regulated pressure acting on the larger diaphragm A, would essentially move the whole piston assembly upward, thereby preventing entry of gas into the pressure regulator. Whereas if you note the spring force F, which was represented as spring S1 in the line diagram, is the only force which is pushing the diaphragm down, thereby the piston down, allowing the entry of gases into the pressure regulator. Hope this was helpful. Thank you.